Hey physics fans, my name is Vernier Barlow. This is my video report on Lab 2, Motion of a Falling Object, which is basically all about gravity and drag-induced motion. The point of this lab was to quantify motion of an object as it is affected by only gravity, and then by gravity and drag force. Then, to understand how each case works with the application of Newton's second law of motion. In order to show this, a Chick-fil-A takeout bag was dropped. The motion was analyzed using tracker and then modeled through VIDLE. The computational model and experimental model were then compared to understand that there was a net force acting on the system and that the object had reached terminal velocity. There are two main principles that are applicable to this lab, Newton's first and second laws of motion. Newton's first law states that an object in motion will keep moving uniformly unless acted upon by another force. In this lab, the object does not move uniformly because it is acted upon by other forces, gravity and drag force. Taking that further, we have Newton's second law, which is force equals mass times acceleration. Deriving that, we get velocity final equals velocity initial plus F net divided by mass times delta t. Here the net force is not zero, and we know this because there is not constant velocity. There must be at least one agent in the surroundings that is affecting the system. Agents here are the weight force from the Earth and the drag force. The object will accelerate at a rate inversely proportional to its mass. This is the video. The Chick-fil-A bag is the system and everything else is the surroundings. The points are plotted here on the right, and the graph turns out to be curved for a while, which shows that there is acceleration. Then, the slope is constant, which means there is no acceleration and that the bag moves at a constant velocity. The axes here were tilted at a degree of 1.1 to account for the slight right movement of the bag. Only the y-axis matters in this lab, and the x or z are irrelevant. I chose the positive y direction to be up and the negative to be down. We take the data from tracker like initial position and final time and plug that into the skeletal code that was provided here, along with the ball's mass and the gravitational force. Along with that, we also plug in the same velocity and position equations from the previous lab, which can be found on my YouTube channel. This line, equation, and assignment statement are essentially Newton's second law of motion. When this model is run, with the weight force being the only force yielding to the net force, we get this. The model's predictions are very different from what happened in the experiment. The bag in the experiment actually moved a lot less than what was supposed to be, according to the model. The model overpredicted what happened. The reason for this discrepancy is because the weight force was not the only force acting on the bag. There's also the drag force. Before I show the model with the drag force, I want to mention another thing. I used the kinematics equation to check the final position of the object with only the weight force after it falls to make sure that the model does an accurate job predicting the object's motion. This is the fundamental equation for kinematics, one of them at least. And the equation, after plugging in values, gives a value of negative 7.9 meters as the final position, which is the exact same position the model gives as seen here. Drag force is accounted for in the code by using the turbulent force equation containing the proportionality constant b and the ball's velocity squared. B was chosen by matching the model's final position with the observed motion's final position. This equation can be written like this in the code. In the code, we can see that the proportionality constant b is set to this value, the drag force equation is here, and now the net force is the sum from the weight force and the drag force, whereas previously it was just the weight force. Now let's run the code. As you can see, when accounting for drag force, the model does a better job of predicting the motion of the bag. In the graph, the model of the weight and the drag force is much closer to the experimental position of the bag. In conclusion, we can say that the terminal velocity will be experienced by the object with a large quantity of drag, which is a slowly dropping object that has more surface area and less density. This is what happened in my case. To make sure my bag had terminal velocity, or was very, very close to having terminal velocity, I checked on Excel. I calculated the slope from the experimental position values that I had gotten by doing final position minus initial position divided by final time minus initial time. Then I found the change in slope by doing final slope minus initial slope and displayed those values here. Then I took a few of the values from the change in slope and averaged them because I thought they are what consisted and made up of the terminal velocity, or where terminal velocity was. The average change in slope was found to be 0.002 meters per second, or negative in this case because it was going downward. If I had dropped the bag from a higher point, I'm sure I could have even gotten lower numbers to a point where the change in velocity would be zero, meaning terminal velocity was reached. Now let's answer the questions. What does it mean? The second model, accounting for both the weight and the drag force, does a much better job of showing terminal velocity. Terminal velocity is achieved because the object has enough drag that is equivalent to the weight force, so net force is zero, meaning velocity is constant. Gravity was the prevalent force in the beginning, which is why the graph was curved initially. But later it becomes linear due to the zero acceleration and constant velocity. Question 2. What if just dropping an object will show a graph having downward acceleration? If the object is thrown down with enough of a force, say arbitrarily enough to give an initial velocity of about -10 meters per second, then throwing it down means it will actually have a drag force that exceeds gravity. So it will end up decelerating first, as seen here by this arc in the graph. But eventually, F net will be 0, and then terminal velocity will be reached once again as the graph keeps going, as you can see by this linear portion of the graph.